Hello, everyone. I am Jafari. I'm a postdoctoral associate in the Laboratory for Information and Decision Systems at MIT. And I'm going to talk about our research on flow batteries degradation and specifically on an optimization algorithm for flow battery capacity restoration. We all know that there are a number of factors impacting the techno-economics of battery energy storage. And one of these main factors is degradation. In an energy arbitrage market, lithium-ion battery systems can lose 12 to 46% of its revenue due to degradation, depending on the technology and the market. However, in flow batteries, they have longer lifetime compared to lithium-ion battery, and it may change the merit order for this technology in the future. Flow batteries are one of the emerging technologies in the energy storage area, and it has decoupled power and energy capacities and also longer lifetime. So when we cycle the flow battery, we lose some capacity, which means we lose revenue opportunity. However, we know that part of that lost capacity can be restored by electrolyte rebalancing, which we name it capacity restoration service. If we look at this figure, there is a part of capacity fade which is irreversible. We cannot do anything about it, but the reversible capacity fade can be restored by mixing the electrolyte tanks. And the objective here is to optimize the number and time of these services to minimize the service cost while maximizing the revenue from energy arbitrage. So to solve this problem, we developed a simplified linear version of the problem. We have some assumptions such as fixed daily price variations, which means we have constant arbitrage opportunity in all days. We assume linear capacity fade with respect to cycling, and also one mandatory service at the end of period D. Also, we have some basic definitions. We define K as cost of each restoration service. X is number of services inside period D. N is number of days in each service period. Q is restorable capacity at the end of service D. And finally, R is daily arbitrage revenue. So we developed this problem and we try to see what is the cost of these services versus the revenue opportunity we can gain. So imagine if we don't do any service in period D, the lost revenue opportunity will be equal to the area of triangle ABC in this figure. However, if we do regular services, the lost revenue opportunity in X number of services will be the sum of areas of smaller triangles or dotted triangles. So the total opportunity that we can gain from doing X number of services will be the area of bigger triangle minus the smaller triangles area, or as we show in this equation. And if we develop the final equation, the net revenue opportunity for each number of services will be as shown in the last equation. We can show that this equation is convex and it has only one solution. And if we plot this equation for different number of services, we can see that the optimal number of solutions is only one number. So it has only one maximum. And also we can observe from this figure that for different ratios of cost versus the potential revenue, we have different optimal number of services. We can solve this problem. We can find the optimal number of services with respect to the revenue opportunity and also cost of the services. So from these figures, we can see that the linear version of problem has an optimal solution. So we move on and try to develop the complete problem in an optimization form. So we developed a mixed integer linear programming formulation for the problem. We assume at this time that the service periods N1 to Nx plus 1 are not necessarily equal. So the objective is to optimize both the number of services and also time of each service. So here we have the objective function equal to annualized arbitrage revenue in different years minus the service cost and also minus the operation and maintenance costs. This objective function is subject to a set of constraints. We start with the constraints related to the service. We define a binary variable as B equal to number of services. And we assume that at the end of period D, we have one mandatory service. And then we define the degradation based on this binary variable. So in the days that we have binary variable as 0, the degradation happens and the capacity declines over time and cycling. However, on the day of service, we restore part of the lost capacity. We also consider that we don't have cycling in the day of service. So the day of service is off day. We don't have revenues from that day. And also we define an upper bound for the number of services. Of course, we have other operational constraints for the battery as its efficiency, its state of charge, and power limits. With this formulation, we can solve the problem and we can find the optimal number and time of services for capacity restoration or electrolyte rebalancing. However, there is a problem. This problem in this form is very inefficient computationally. When we define conservatively a large number for upper bound of number of services, the solution set becomes extremely large and it takes a long time to solve the problem. So we propose a two-step optimization algorithm such that instead of solving the problem for whole solution set, we first find the optimal number of services with fixed service days. So we assume that N1 is equal to N2 to Nx plus 1. After finding an optimal solution or range of optimal solution, we find the final optimal number of services and their times. So you can see in this algorithm, we initiate with some values for revenue, number of services. Then we run the optimization, linear optimization for set of simple assumptions. We calculate the revenue, and as long as the revenue is ascending, we assume that we can have a better optimal solution. And when we get to the maximum revenue and revenue start to decline, we pick that number of services. We assume a reasonable bound for number of services, and then we run the complete problem for a smaller set of number of services. So with this algorithm, we want to show an illustrative case study for a vanadium redox flow battery using 2 years of day-ahead market price data from New York ISO. We show how it works for different service costs. For illustrative purposes, we picked $500 and $200 as two values for service cost. We also have some assumptions for the capacity. It's a 0.25 megawatt, 1 megawatt hour battery. Charge and discharge efficiencies are from experimental data. We assume a calendar life of 10 years and cycle life of 20,000 years. End of life criteria is 30%. And the discount rate, annual discount rate is 70%, and variable O&M cost will be $0.3 or 30 cents per megawatt hour. With these assumptions, we show some initial results. Well, for different service costs, you can see that we have find optimal number of services in 2 years. So optimal number of services is 2 and 3 for $500 and $200 service cost respectively. So you can see the bar graph is the optimal number of solutions. For smaller numbers than the optimal number, the arbitrage revenue opportunity is lost due to the faded capacity. And for bigger or larger number of the from optimal number, the revenue increases slightly. However, the cost of service is bigger and revenue cannot compensate the added service cost. Also, we show that with this optimization, the algorithm is successful to pick specific days for doing the service. When we have $200 of service cost, we have like 2 service days in 2 years, plus the one last mandatory service. These days are 201 and day 536. You see that these intervals are not necessarily equal. And the days between these services show that the algorithm can optimally pick the best time for doing these services while keeping the revenue in its maximum value. So in summary, we can say that the problem was to optimize the vanadium redox flow batteries electrolyte rebalancing service time and service number. We analytically showed that the simplified linear problem is convex and it has only one solution to maximize the revenue. Complete problem can be formulated in MILP form, but it is computationally expensive. So we proposed 2-step optimization algorithm to improve the computation time, while we made sure that the optimal solution is obtained. Now we are working on the algorithm to improve the VRFB model that we have used, and also we want to improve the computational efficiency. These are some of the references we have used throughout this project. Thank you for your attention. I will be glad to see your questions. If you have any questions, please send me an email. Thank you.